Now, for all the people just joining us, we have our first lecture coming up by astronaut Gerhard Thiele. He was selected as an astronaut in 1987, and he's a German astronaut, and he went up in space for 11 days in the year 2000 to work on the cartography of this here Earth. So, in just a minute, we'll hear his lecture, and yeah, then we'll take a short break. So, yeah, just make yourself comfortable and enjoy the lecture.
Thank you very much for the kind introduction. And ladies and gentlemen, I must admit it is a little bit difficult to use these words if I see all the young faces. Normally, if I say that, they are typically more my age when I give this talk. But anyway, I am glad that you decided not to spend the time outside and walk through the solar system as I did just before the lecture here. I would like to share with you some thoughts, and it is not so much about my space flight. It is more difficult. It's not difficult to tell that I am a little bit older than most of you in the room. So I am past 60 already. And that means that you not only look forward into the future, but you also look more often back to what you have done and sometimes to what you have not done. And so the next 40 minutes or so are more a reflection on things that I have learned during my career as an astronaut. Nevertheless, I would like to fold this into that mission that I know the best because I was part of it. And the talk is titled Another View of Earth. And it is a translation of the German Ein anderes Bild der Erde. It has a double meaning. Why? The first meaning is very obvious. At the center of the mission that I'm going to show you was to really remeasure the Earth. When in 1998 I was asked to join that scientific mission. One of the first questions by my co-brick, the lead scientist, was, which is the best known body in the solar system? And the obvious answer should be the Earth. But then we thought, well, I hope this thing stays there. Then we thought, if it would be the Earth, we probably wouldn't fly. So we were thinking a second time, and it turned out it was Mars. Mars at that time was better known than the Earth on a global scale. And this we changed, and therefore this changed our view on the planet Earth. Since that flight in 2000, we know in much more detail how the height profile of the Earth really looks like. But what I would like to get across during the next 30 slides or so is the understanding it is sometimes very helpful to step back from what you are doing today and take an outsider's view on your subject, in this case the Earth, and that also changes your view on things. Maybe the best example I can give you, and that you may have experienced, is if you go to a museum and you look, for instance, at a painting from the Impressionists, Claude Monet, for instance. If you go very close, you see each pen stroke, each stroke of a brush, and you can tell it is there because the master wanted it to be exactly at that place, but you have no clue how the entire painting will look like. And in order to see that, you really have to step back. And in a very similar way, when we want to understand Earth and how we have to protect our Earth, it is sometimes helpful to stand back. But with that, I would like to come to my first slide, and this is the crew now, or the team. big misunderstanding is often that people think spaceflight is done by astronauts. Now, nothing could be farther from the truth. Why? Of course, the astronauts are the ones who are always visible. Because if a shuttle flies into space, or a Soyuz rocket today, or in China, a Shenzhou rocket, then the cameras are there and it makes the front views. And if someone has the black, red, yellow stripes, then ARD, ZDF, RTL, and how they are all called, are there, and you make it to the front newspapers. And that gives the impression astronauts do spaceflight. But in reality, we are only a very small part of a large team. And in our case, there were 300 scientists, engineers, and technicians who prepared that very mission for 3 years before we actually flew. We came on board only 1.5 years when a lot of the preparatory work had already been done. And of course, in our case, 11 days, we are the ones who have to put things in the end together and hopefully get the data back that the scientists were hoping for. But the key thing is, we can do that only because several hundred people have really worked with their Herzblut, Herzblut, as we say in German, for a long period of their life to make something like this, like a space mission happen. In this specific case, to measure the Earth. And having said that, the best picture that I can give you is the astronauts are a little bit the tip of the iceberg, and the iceberg is only visible because there's a huge body below the water surface that actually lifts it so that it is visible. And in the same sense, astronauts are visible for 11 days. As I said, the preparation of the mission was 3 years. The reduction of the data and the publishing took another 2 years. So the entire mission took 5 years. 300 people for 3 years, roughly 30 people for 2 years. And when people talk about the SRTM mission, they mistakenly only mean the 11 days we have been in space. And that is obviously an important part, but it is not the mission. And this is what I would like to drive home. But with that, I would like to come to the 6 phases here, because you will see them more often. And I will be politically incorrect and start with the 2 guys in the middle, in the background. This is Kevin Kriegel. On the left, the commander. He flew on his 4th flight, the 2nd time as a commander, and Dom Gori next to him was the 2nd time a pilot. And for those who are familiar with NASA, understand that if the 2 front seaters, as we call them, are both experienced in their role, something special must be the case with this mission, and I will come to that later indeed. With that, I come to the ladies. On your left side, you see JV, Janice Voss. I will say JV because Janice and Janet on the right side. Janice, Janet, if you call that, you have the same as you have at home if you have kids. Either no one comes or both come. Mostly no one comes, so we have to change how we call them. So I will frequently say JV because this is just how I know her. She was on her 5th space flight and the most experienced of us. And Janet was also on the 2nd. By the way, the 1st she did together with Dom. Mamoru also was on his 2nd flight, and I was the only rookie and therefore the newcomer. And the most important task the newcomer has is he has to design the crew patch. Now, that shows you very clearly I will never become an artist, okay? But nevertheless, there are a few things I would like to talk about. The crew patch, of course, has to depict to some extent what is this mission about. And you see the shuttle. The shuttle with the open cargo bay looks down towards the Earth. You see a long structure, a mast, coming out of the starboard side of the cargo bay. In reality, it was 60 meters long with a secondary antenna. And you see illustrated radar beams, which we used to observe the Earth. Normally, the Earth is, if it's not night, where you can't see anything, you can't see anyway nothing in the visible light range, but also during daytime, most of the Earth is covered with clouds, so you can't measure anything if you would just take regular photographs. So that's why we use radar beams, and radar can actually penetrate clouds, and this is seen here. You see the Gulf of Mexico, which is penetrated by the radar beams. But more important for me is something else. There are a lot of stars in this image, and you will not be surprised that I, as astronaut, I am of the opinion that space is an important step of our way into the future. So we are, if we look at our theme, global justice, I think space can play an important role with that theme as well. It is not the most important step, don't get me wrong, but it is a step that we must not neglect. And I say that especially to the young ones here, because you are the ones who will determine how our future will look like. And it is especially important for Europe and Germany to not turn the back on space activities. And the best symbol for our future we could think of are actually our young ones. And therefore, the stars resemble the kids that we have. So Dominic has 2 kids, here they are. I don't know who is who there, unfortunately. I forgot this detail. I think this is Kimi and Tim, but I'm not 100% sure. These are the 2 of Janet Cavendy. These 4 are ours. Kevin had 4 kids, and Mamoru had 3. Now, JV was the only one who was not married, so we said, that is a difficult thing. With the symbolism, we can't leave her out, so what are we going to do? So we said, very clever, we give her a rising star. So the future might change. Well, it's still true. She never got a child, so the depiction is still okay. I need to say something about 2 stars. This is because I made a promise. This star was 10 years young when I flew into space. It's Finn, our youngest son. Today he is 26. And at that time, he complained and he said, I'm a Cavandi. My star is much closer to the Cavandis, and no one will know that I belong to you. So he asked me to move that little star more towards the name Thiele. It was too late. So I had to tell him, Finn, I'm sorry, I can't change it anymore. So he asked me to promise whenever I show it that I tell everybody that this is Finn and he belongs to us. So I did that today as well. And normally I don't say that, but because it was just recently in the news, some of you may have heard about this selection, Die Astronautin. In Germany, a private group selected their first private women astronaut. It is high time that one of them flies, and one of the 2 is actually she, Insa. So our daughter stepped, so to speak, or follows me, hopefully. We will see. Has anyone seen a shuttle launch? Not on TV, but in reality? No one. I don't see any hand signs. Sorry. I was looking here in the back. It's something extraordinary, is it? Very extraordinary. I personally believe from the outside it is even worse than from the inside, because from the outside you want to help that thing get off. It goes so slow that you think it never makes it. It feels completely different if you are inside, I can tell you. I have seen 8 or 9 shuttle launches a day at night, but every single one is absolutely spectacular and breathtaking, to say the least. But what is really breathtaking is the view that you see here. Normally, the shuttle that flew the last time in 2011. It's already 6 years ago. I can't believe it that it's so long ago. But normally when it was prepared for launch, you never could see it. If you would have visited Kennedy Space Center and you looked at the launch tower, you just saw iron and steel, nothing else. And maybe the two solid rocket motors were sticking out. And if you were looking from the right angle, of course, you could see the orange tank. But the shuttle you didn't see. Why? The cargo bay doors that are closed now were still open until roughly 14 hours before flight, because people were working inside the cargo bay to do the final adjustments and to get everything ready before the cargo bay doors are closed. And this support structure is being rolled back, and then for the first time the shuttle really stands free on the platform, as it should if it wants to get off. And one of the special treats that we have as astronauts is that we can name 22 people, and they are carried in buses in the evening before the launch to the launch tower. They are getting fairly close, 150 meters or something like that, so you can't touch it, but 150 meters, if the whole stack is 70 meters high, is pretty near. But what they don't know is that we are also there. But the crew is in quarantine, which means we can't meet our families and friends. And it's a very special feeling. We are actually not far away. There are some huts, and we stand in the shadow of one of those. And roughly at the end here of the Audi Max, you see your friends walking around. And it's a somewhat special feeling, I must say. Just on the left, right here, would be the elevator that brings us up the next morning to floor 57. And when the elevator doors open, right here, we walk over this bridge into the white room, where we are outfitted. We get our parachute and last equipment before we crawl into the cockpit of the shuttle, where our seats are. And one thing that I remember, it's very well orchestrated. The very first to board the spaceship is, of course, the commander. He is also the last one to leave it, followed by the pilot. And then turn number 3 and 4 was JV and I. So we were standing right there at the end of the bridge, while Kevin and Dom were already inside waiting for the final checks and climbing in. And I asked JV, when you did that the first time, weren't you scared? And she looks at me and said, of course I was. So I thought, maybe the butterflies in my stomach are perfectly okay. It was too late anyway to say, not a good idea, I will go back. So, but to give you an impression on the power that is really released, where were you standing when you saw the shuttle launch? On the causeway? On the highway? How far away? Roughly. Pardon? Couple of miles. On the NASA premises or outside? Outside. Then I am not sure whether you could experience that, but if you stand on the NASA causeway, you are roughly 5 miles, 8 kilometers away from it. And if you're the causeway is long. So you have to stand in the right spot. The shuttle takes off and then turns on its back. The reason why we turn on the back is we have wings. And wings generate lift. And lift is a bad thing because it takes you away from the tank. So we turn upside down, so the lift presses us on the tank. So that is the reason for that. But when it turns back, and it may fly directly away from you. And the only things you see are the 3 main engines, the flames, and also the flames from the solid rocket motors. And you look directly into them. And in your face, it gets warm. So if over a distance of some 8 kilometers, your face all of a sudden gets warm, it didn't get warm when we just saw the experiments here. So you can imagine that that flame is a little bit hotter than what we have just seen. But I don't know how many grams you use. We use 2,000 tons to burn, so that's not exactly 2,000, it's only 900 and something, but anyway. A lot more, as you rightly said, if you use a lot of fuel, then you get a huge flame. The other thing that you notice, when the shuttle launches, it rumbles and thunders, and it is really it is impressive, especially in summer. In July and August, when the temperatures are high and the humidity is high. And high humidity means deep frequencies are transported very well. Everyone knows this. If you just think about thunder and lightning in summer and in winter, they are different. In winter, you don't hear them for a very long distance. Why? Because normally humidity in winter is not very high. In summer, you can hear them for a much, much larger distance, and they can be more energetic or appear to be more energetic. And the low frequencies of the shuttle are transported very well. Again, in July and August, it's hot. The most thing that you wear is a t-shirt, and that means your belly begins to move. And you can feel your belly all of a sudden swinging back and forth, just gently. So that gives you an impression on the sound waves that are coming. And the last thing you see, the clouds on the left and the right. These clouds are water clouds, but that water doesn't come from the tank of the shuttle. The tank contains liquid oxygen and hydrogen, which we burn into water, but that's not the water that we see here. Beneath the launch tower is a huge basin, and that basin is filled it contains several swimming pools of water. And when I was asked why is that water there, the natural answer is, well, this is burning very well, so it's good to have a lot of water there. But that answer is wrong. It has nothing to do with fire suppression or prevention. The reason is sound suppression, because if there would be no water in the basin, the sound waves that are reflected would destroy the shuttle before it even has taken off. So you need the damping of the water. The water is heated and it generates clouds, gas, so to speak, water vapor, and that energy means it is not reflected, and therefore the shuttle can safely take off. But these three things give you an idea on the energy that is being released. And if Kevin would be here, our commander, he would say, if the solid rocket motors ignite, you know that something very significant in your life has just happened. You just don't know how it turns out. And you feel a little bit like that. It is impressive indeed. But only 8.5 minutes later, we are in orbit. Now, I am not long enough here in Ilmenau, but 8.5 minutes from here, you can't go very far. It was roughly the time it took me by car to the hotel somewhere downtown. So space is not that far away, just 8.5 minutes, but only in our mind it seems to be so far away, and I am quite sure the young generation is going to change that. This image is taken from the flight deck of the shuttle. We are looking to the back doors into the cargo bay, and we see the antenna structure filling the entire cargo bay almost completely. We see a canister, which was roughly 4 meters long and 1 meter wide, and it contained the 60-meter long mast, this structure that you see down here on the right, which was collapsed by a factor of 15. So 60 meters divided by 15 gives the 4 meters inside. And for me, it's an absolute miracle how you can bend such a structure into such a small container with all the cables and the electronic equipment that comes with it, extend it, and then in the end bring it back in again. That by itself was an engineering masterpiece. But the thing that is, there are two things really important for me. The first one, the image was taken roughly 5 hours into the flight, maybe a little bit earlier. And why are these 5 hours so important? If you think back, hardly anybody has witnessed that time. To the early 60s of the last century, the first American to really circle the Earth was John Glenn. He flew 3 times around the Earth, and once around the Earth takes 90 minutes, 1.5 hours. So 3 times is 4.5 hours, which means after 5 hours, he was not only back on Earth, he was already picked up by one of the aircraft carriers, and he was with his capsule already on board of an aircraft carrier while we were still preparing our experiments. We have not even started measuring things, we were just building things up. The point is, in these 40 years that happened between his flight and our flight, things have changed dramatically. In the beginning, space or going into space was just to survive. Can we do that at all? And can we bring them back? These guys were real heroes or crazy. It depends on how you look at it. We did not know. And John Young, who flew 6 times into space and walked on the moon, he said, I heard him once saying, we did not know what we were doing. And more often than not, they were just lucky, fortunately. But today, I'm not saying we have mastered it, but we at least are able to send people to space, not to just be there, but to live and work. Well, so we send people to space to live and work, and as we speak, 6 people are on board the International Space Station right now. So that is one part that I want to drive home. Spaceflight today is very different from what it was 50 years ago, and in 50 years, spaceflight will be totally different from what we are seeing today. Maybe in the question section we can come to that. And the last thing that I want to show, just look at the Earth, and you may guess what this blue line is that separates the Earth from space. That is our atmosphere. Now, the film actually sees more than the eye. It's actually not as thick as it looks like here. Our atmosphere is roughly 10 kilometers thick, by and large, you could say that. If you just collapse the entire air into one layer with equal density, it's roughly 10 kilometers thickness that you get. And at pressure, at the normal pressure that we have. But 10 kilometers on a sphere that has a diameter of 12,700 kilometers. Now we are at a technical university, and that means 10 to 12,700. That is not a very large number. It must be very small. But how small it really is, you cannot express that in numbers. You need to see it. You really need to feel it. And for me, it looks like, I had the impression you just make and the atmosphere floats away. That's how thin it really looks like. Man sieht nur mit dem Herzen gut, das Wesentliche ist für das Auge unsichtbar. You see only the important things with your heart. The most important things are invisible to the eyes. This is what the fox says to the little prince. And I never felt the truth of these words when I was looking to our atmosphere. Now, I would like to come a little bit to the point, how do we actually do this when we are up there? I mentioned already we used radar beams. I will go in a little bit more detail than that. But of course, when you go up there, you cannot say, okay, work starts at 9 o'clock, 5 o'clock it's finished, and I come back next day at 9 in the morning. So we work essentially around the clock, and that means being 6 people, we work in 2 shifts of 3. Now, I also said it takes you 90 minutes to go once around the Earth. That means 90 minutes, you have a sunrise and a sunset. That is 45 minutes daytime, 45 minutes nighttime. That would be an awfully short shift if you say, I work the day shift or the night shift. So we call the shifts red and blue. And I was together with Janet and Kevin in the red shift, and correspondingly Dom and Mamoru and JV were on the blue shift. And also 24/2 is 12, so one shift is 12 hours, but that is only part of the truth, because you of course have to have handovers before and afterwards, and there are some maintenance tasks that you normally don't do on your shifts. So your workday is roughly 15 hours. For 11 days, no Saturday, no Sunday. So I ask, who can work for 11 days, 15 hours a day without making a mistake? I can't do that. That means you are most likely going to make a mistake. And that is the biggest fear that you actually have, because you know that there have been hundreds of people working for this mission for many years, and now you are the one who can screw things up. So one of your biggest concerns is actually that you do the wrong thing. And there are 2 things that help us, or several things that help us actually, but 2 come to my mind right now. The crew, don't ask me how that works, but you develop a communication scheme that is very special and that is unique to some extent. I heard twice during these 11 days, Gerhard, are you sure what you are about to do is what you really should do or want to do? So if you hear these words, you just take your hands off and you think again. And then I said, thanks, Kevin, and thanks, Janet. And that happens without them really looking over your shoulder. Somehow you realize something is about to go wrong here right now. And then the key thing is you have to speak up. And Kevin, our commander, also heard that. So if he would have been a commander who said, how dare you question my authority, things wouldn't have gone very well. So he also took his hands off and he said, thanks, Janet, for instance. So one of the things when you work on so delicate tasks, you really need to learn how you can master these challenges together. And here again, I come to the global justice theme. If we want to master the challenges that we face together, we have to learn a little bit better how to work as a team. I mean, the team idea is not applicable to societies in the same sense, but I think you get the point. One thing that we definitely don't do, if something goes wrong, we put oil into the fire. That's what we not do on a spaceship. We do it here on Earth, yes, but that's a different issue. The other thing that helps us are these procedures, these white books that you see here, for instance. Of course, it is indeed true. We are trained so well that in principle we know every step by heart. So we should not, we are not forced to use the procedures, but you just double check that what you are doing is exactly what you are supposed to do. The procedures have their advantages. They confirm that you are on the right track. They have their disadvantages, not so much in space, but more in your private life. My wife always complains, since he is an astronaut, I have to write for everything a procedure, and not only that, I have to even train him now. So even for simple things, I will not go into these details. Now, no, not yet. Our main interface to the radar equipment that we had in the cargo bay were mainly computers, as you can see here, and several more procedures. The key computer was this one. And this key computer was measuring the distance between the two antennas, and why this is so important we see on this slide. Now, this slide looks very complicated. I will not go into all details, but I ask you not to fall asleep right now. I will tell you when you can relax again a little bit. I said we wanted to measure the height profile of the Earth, and what we and this is symbolized here. How can you actually measure the height profile of a planet from a satellite? And the shuttle for that purpose is nothing else than a satellite going around. Now, we start at the very bottom and you see a mountain range. This mountain range actually exists. It's in New Mexico, in the United States. And imagine we would just like to measure this tip, the height of this tip above the sea level, or as an engineer would put it, the length of the yellow arrow set. And we go now counterclockwise to the right on the screen. You see the shuttle. You see a blue, red, green triangle. And if you know the height of the shuttle, h, as it is depicted here, with good accuracy, and if you know the parts of the triangle, you can easily compute the length of z. It's not a big problem, actually. It is a very simple thing to do in principle. In practice, it's a little bit more complicated because the Earth is not flat and the shuttle is moving and not standing still, so you have all kinds of effects. But the principle is fairly straightforward. To give you a feeling for the task, we were flying at a height of 235 kilometers, and we needed to know the height with an accuracy of 1 meter. So that is actually quite a challenge. That is 7 digits accuracy that you need to have, or 1 part in 10 million. And this was not done by us, it was done by the ground. Around the Earth were 17 radar stations that continuously followed the flight path of the shuttle, and it took some 2 months to reconstruct the exact flight path of the shuttle. So we had H continuously available. And then let's look at the triangle for a second. You can imagine if the distance between the mountain and the shuttle is on the order of almost 400 kilometers. Remember, 235 goes down. We are looking to the side, so it's a little bit more, roughly 400 kilometers. The two antennas are not exactly at the same place, fortunately enough. And that's why we have 2 different distances, and therefore they are in blue and in red, symbolizing that they are not exactly identical. They are almost identical, but there are slight differences up to 1 centimeter or sometimes even a little bit more, depending on the terrain. That can be measured. And if we now would know the length of the green B, we call it the baseline, the distance between the 2 radar eyes, so to speak, then we can easily compute the length of Z. And so we had on board to measure B, that was that one computer. It was 60 meters long, and if I would ask not a chemist, but even a physicist or engineer to build here outside a distance 60 meters long and measure that with the precision of 0.5 millimeter, then you would use some equipment. I mean, you would not use that just by a ruler and say, we now know that it is 59.9 9 meters or something like that. You need some laser lights and whatnot. So that was indeed the biggest challenge. And every moment, a radar beam that you send out and it comes back and the two antennas record the signal, every moment you need to know what the distance between the two antennas is. And we were sending out 1,400 signals per second. So essentially, we had to continuously know what the length of B is, and that was the biggest challenge for us as astronauts. Now, if you go further to the left, in the upper left of the screen, you see two radar images, and I hope for you they look alike. At least for me, they look almost identical, and they better should look almost identical because the blue R and the red R plus delta R are almost identical. So why should the images of the two antennas be fundamentally different? But if you look at the minute differences by subtracting the two images from each other, you can see the difference, as the radar engineers call it phase information or interferogram, but you could, if you know that the sea level is 0, you just add all the phase differences up as the terrain rises, and you can convert it into information like we know from our atlases, or even make a three-dimensional elevation model as we see down there. And with that, you can relax again. Now, a few images that show you what can be done. This image shows you two satellites composed. On the right side, the satellite is called Landsat. This is Oahu in Hawaii. And you can see there are mountains. The white stuff is not snow, it's clouds, but you have no information how high these mountains are. This information is coded in the colors on the left. This comes from our mission. I leave it up to you to decide which of the two images is more appealing for the eye. But if you are interested in how high the terrain really is, you need to go to the left side of the image. And here, we are not too far from here in Europe, a little bit further south in Switzerland. You see the Vierwaldstätter See up here, the Genfer See down here. The white, again, is not snow, but anything that is above 4,000 meters. So it's just a color coding. And what can be done with these data can be shown on the next image. This is actually the region where the river Rhine begins. And we are in the Alp Mountains with the resolution as the Earth was known before our flight. And this is actually the time roughly of today when the snow is melting. And this is a simulation. How is the area drained from the water? And you saw the water flows either north, south, or east, west, and not much in between. Now, this is the terrain, how it looks like after our flight with a much, much higher precision. And you can see that the simulation of the water runoff is much more precise. That may sound like a nice little thing, but for the people who live, for instance, in Cologne, where on a very regular basis the Rhine goes outside and enters the old city, for the people living there, it is really important if you tell them 24 hours in advance what is going to happen, so that they have time to carry their stuff to the first floor. Of course, when you are up there, you have to accommodate other things like living. You have a problem with two people. The two people that you have a problem with are the commander and the pilot. Why? Going into space takes 8.5 minutes. I said that. If you add 2 hours for closing everything down, shutting everything down, and turning the spaceship into a laboratory, their workday after 2.5 hours is done. And then coming back takes an hour plus an hour preparation. It's also 2 hours. That's a cool job. You start 2.5 hours, then you have 11 days nothing, and you have 2 hours in the end. You need to keep them busy so that they are in a good mood all the time. And So Kevin and Dom were responsible for cleaning and cooking and this kind of stuff. And here Kevin inspects filters. We have no convection in zero gravity. You have not the normal convection. So we have forced circulation by fans. And forced circulation means you have a constant airflow that always goes in the same direction. And certain things gather always at the same places, including cameras, by the way, that were not properly fixed somewhere else. So the good thing is you know where these things are when you have lost them, but someone takes good care of them. Kevin was also the one who was our cook, the redshift cook. And I know you will probably not believe it when you look at me, but I had, well, people said, Gerhard can eat a lot. And Kevin said he is normally a very pleasant guy. The only thing we have to take care of that enough is going in here. And then he is a happy camper. And he came on day 8 and said, we have a small problem. I asked, please bring me something to eat. And he was going in the middeck preparing the food. 20 minutes later, he came back. We are out of chicken teriyaki. I forgot what it was, but I said, no problem, bring me something else. I was raised by a Swabian mother. You just eat what is there and you don't ask questions. So he said, we have a bigger problem. I said, what is the bigger problem? He said, no blue food left. Now you need to know that every astronaut has colored food, and my color was blue, so all my food was gone. And I had food for 13 days, 11 days plus 2 days in reserve makes 13 days food, and I managed to eat all the food in less than 8 days. I survived, otherwise I would not be here today. But a short, interesting moment. Now this is our official crew photo from space, and don't think that we have put the camera at the ceiling and we are carefully lying on the floor in a star. No, in zero gravity, you just take the position that you want. You would not be seated like you are seated now. Everyone would by now be floating anywhere here in this room. And so you just arrange yourself in a circle, and that's it. Up is where your head is, and down is where your feet are. So you determine, so to speak, the orientation yourself. And actually, that is quite helpful. One thing that I remember, we had what was called the Personal Preference Kit, PPK, and it contains your toothbrush, your hairbrush, mine probably not, but a shaver and the things that you need. And because hygiene is very important, it was very clear that these things are in a certain place and they stay there. And so you get out of your sleeping bunk in the morning, not fully awake, you grab there. And one morning I grabbed and it was air. Nothing. So I looked, no PPK around, and I was searching for the thing, and I couldn't find it. So Kevin noticed it, and he said, just turn around. And he gave me a small push, and I turned around, and I was upside down. I mean, up was where the head is, but with the normal orientation, I was upside down, and I started to look again. Here it is. You are in a new room when you change your orientation and you see different things, and what you are looking for all of a sudden springs to your mind and comes in view. And it did not only happen to me, it happens to everyone, and you use it simply as a tool if you are in such a situation. By the way, the shirt that you just saw is exactly the same that I am wearing tonight. Not a similar one. Now, the Americans are normally very polite, but sometimes, well, I almost had said that was true until a few months ago, but they are normally very polite, but they can be very clear in their messages as well, as we are learning. And so every crew gets from those who trained you a nickname. And that nickname can sometimes, it sticks to you, and sometimes you don't want to be nicknamed like that. So you are always a little bit concerned about your nickname. And there's a huge ceremony with speeches and everything, and a cake. And when our nickname was revealed, big relief, we were the chocolate crew. Now, why the chocolate crew? Rumors had it that 5 out of the 6 could easily survive 1 week on chocolate only. And I was one of them. JV was also one of them. I actually forgot who could not do that. Probably Mamoru, but I'm not 100% sure. So, a few, we of course, not only took images of the Earth with radar, but also with regular cameras. I mean, there are now a few images that I would like to share. This is the delta of a river. Some of you may have recognized it. And what you actually see here, this dark blue, this is the Nile River. And this area, this dark area is where you normally have flooding. And the desert is, of course, clearly visible. But the reason why I show this, now I hope my hand is quiet enough. These are these 3 points right here. I know where to look, so I see them right there. These are the pyramids of Gizeh. And these are the only human-made buildings or objects that you can see during daytime. Now, during night, of course, it is different because light, I mean, that is, you see everywhere. Our planet is almost light polluted in certain areas. But during daytime, the pyramids are the only structure that you actually can see with your naked eyes. You can't see cities. It's impossible. You can't see the Chinese wall, for instance, despite the fact that many people think that you can see it. But the Chinese wall is simply too narrow. It's only 20 meters wide. The pyramids have more than 100 meters at the base. So there you have a chance. And we were lucky because we didn't see them the first time either. It was actually during the 5th time when I actually saw them. And I only saw them, I believe, because we were flying over the Middle East during sunset. And sunset means the sun angle is very low, and that means the shadows are very long. And the first thing that we actually saw were the shadows the pyramids were casting, and not so much the pyramids themselves. And then when you see the shadow, you just go back at the shadow until the base, and there you can see them. So the only thing humans have made that you see by daytime. A sunset, beautiful. But when I saw this image after the flight, I said, this is not what I have seen. What is this? Now, at the bottom you see the Earth, at the top you see space, and then you see the colors of the rainbow. And actually, what you see in space is indeed a rainbow, but timely separated. It starts with a blue flash, just like a blink, just like a blink of the eye, a quick flashlight. The next is green, followed by yellow and orange, and then comes red. And the whole thing lasts 20 seconds. So it's not like a sunset here in Ilmenau. If we go after the lectures outside, we might get a beautiful sunset for 45 minutes or something like that. 20 seconds and it's done. Actually, the blue flash not, but the green flash you can see down here on Earth. So it's not a phenomenon that is typical for space. It has to do with refraction of light in our atmosphere. And if the air is absolutely clean and you have no contamination, that generates actually the longer wavelengths of the red light, then you don't see red light, then you actually can see the green light. So you have to go to North Norway, North Sweden, North Finland, or to Alaska or Canada. And when you there look at the ocean or over the ocean at the sunset, then you can actually see a blue flash. And for the YouTubers, you just look at green flash. You look at green flash on YouTube, and then you can watch it also at least on TV. So it can be seen here. This green light actually is a different phenomenon. It is called air glow, and it happens in about 80 kilometers above the surface of the Earth. And it's, for me, a perfect example on how science works. The simple explanation is, at that height above Earth's surface, we have free oxygen atoms. No molecules, but atoms. These atoms, during daytime, absorb the energy of the sun, and during the nighttime, they release the energy, and that is the green light. So far, so good. That is perfectly okay. However, if the explanation would be that simple, every astronaut should see that during the nighttime, right? And we did. 11 days at night, we saw air glow. Beautiful. However, there have been astronauts who have flown 5 times into space. They spent 40 days in space and longer. They never saw air glow. So there are other mechanisms involved in that as well. And the key the key thing that I just told you are not necessarily is not sufficient to explain the entire phenomenon. And I talked to Alexander Gerst, who spent 6 months in space, and he saw it only on 3-4 days, for instance, just as an example. For those who like to look at the stars and constellations, you see the Orion setting over South America. This is my favorite image. Favorite not because it is particularly nice, but because it sends me right back to a very special moment when you fly from day to night. Again, from day to night, it means that the sun is setting and is casting long shadows on Earth's surface. And regardless whether you are over the ocean or whether you are over continents or whether there are clouds or no clouds at all, it is just a miracle what is happening in front of your eyes. It is a sheer beauty that you can see there. And in these moments, it's extremely difficult to keep your attention focused on the equipment, what you are supposed to do, and not look outside the window. But after 11 days, our flight was over. We were extremely fortunate. We had 2 failures that we encountered, and we were able to recover them in the time we had, because we were measuring only the deviation or the height of the Earth, which means the continents, not over water. The failures occurred over the oceans. And the big one occurred just when we left Japan to go over the Pacific Ocean, and we had 1 full hour over the water before we needed the radar again. And just in time, we were ready and for the next data take. So we were simply lucky. Sometimes you need to have luck in order to be successful. We recorded more than 99.8% of the technical possible data. When we asked the scientists, how many do we need to bring back so that that you welcome us to your institute after the flight, they said, 70% would be really great. 60%, if it's the right 60%, we can live with 60%. But anything less than 60% would be difficult to sell as a success. We came back with 99.8%. Not because the 6 were so good, but because the entire team was so good. And everyone helped to prepare that mission in the best possible way we could ask for. And we had fantastic support while we were up there from the people on the ground who accompanied us. I would like to come to a close with a very brief outlook, a very personal one. What comes after the not the shuttle and not after the ISS. You know that we, in '69, Armstrong and Aldrin went to the moon for the first time, and after 3 years in '72 was the last flight to the moon, and humans never ever have left low Earth orbit, so to speak. We were just circling the Earth as we are doing now. And as a matter of fact, I mentioned the International Space Station. Right here it is. So here, this white dot is the International Space Station. It looks as it would circle the moon, but no, it's circling the Earth. But just in front of the moon, this picture was taken. But of course, I show it because the next step will be the moon, and you will all see it. I predict within the next 10 years, roughly, maybe 12 years, we will see humans going back to the moon. And they may not necessarily be Americans or Russians, they could be Chinese. And for me personally, this image has probably changed the view on how we see ourselves in a way as very few images or pictures that we ever have taken has done. It was an image taken by Bill Anders on Apollo 8. You may recall that Apollo 8 was the first flight where astronauts actually left Earth's surface. If here's the Earth and here's the moon, they were departing from here, and in an 8, so to speak, they were going around the moon. And as soon as you are on the far side of the moon, the Earth is out of view. You can't see it anymore. And so when you come around the moon, then at one point in time, the Earth comes into view again. And that's why it's called Earthrise. And if you look at it from a distance like this, you cannot help it. Earth looks like a spaceship. Yeah? It's just a tiny little blue marble in the blackness of space. But if Earth is a spaceship, it means one thing. We are all astronauts or cosmonauts or taikonauts or whatever, no? Akasavans. So maybe it would be wise we take a little bit better care of this spaceship. The humankind and the man will hopefully learn how to do it in a smart way. And this is an image that I admire as one of the most important tasks besides setting the foot on the moon. Everyone knows that. For me, this is really remarkable. We see here Bruce McCandless, and he was the only person to date who actually flew completely by himself, not connected with any wire, any safety wire, through space. I mean, I am not sure that I would be so daring to do that, but he did it. But especially the young ones will see these things much, much more often. We will see many more people traveling to space to live and to work there. And with the onset of the private companies, you all have heard SpaceX and Elon Musk, but there are several others. They will completely change how spaceflight is going to happen. And I predict that NASA, ESA, and all the governmental agencies will face a completely different world in only 10 or 20 years from today. Spaceflight will be done by private companies, and you will make it. You will see it, and some of you might even be the ones who will make that happen. And with that, I would like to conclude and ask everyone to think in possibilities. If we want, and I come back to the theme of global justice, if we want to be successful there and we focus only on the problems, we are never going to solve them. We need to think in possibilities to solve those. And with that, I would like to finish, and I am ready for your questions. Thank you.
Okay, first of all, thank you for the wonderful lecture, and I think we still have some time for questions. So if anyone has any questions that you've always wanted to ask an astronaut, yes, 1 second.
Thank you. Thank you for your lecture. It was very interesting. My question to you is, what was more terrifying? Was it actually taking off or re-entry?
Neither, actually. Well, it was not really terrifying. But of course, you were very well aware that something special is happening, and probably during takeoff it was more prominent. Simply when I launched in 2000, we had the Challenger accident, which was the accident during liftoff, and we did not yet have the Columbia accident, which happened 3 years later. But we knew that, of course, coming back is also not just a piece of cake. And as a matter of fact, well, as we saw, things can also go wrong there. And we knew that coming home, despite the fact that it worked all the time until then very well, would be another point where everyone had to be fully concentrated and not think about anything else but just on what is it that I am doing right now in order to come back. But being terrified is the wrong thing. Terrified for me means I am shocked and I don't know what to do. If you are terrified, don't become an astronaut. It's not a good idea. So yes, I had a lot of respect, and as I said, I had some butterflies in my stomach, but you need to be able to put them aside and clearly think, hey, wait a minute. I learned that from my daughter, by the way, who was just asked recently, why did she choose this job? And she said, she's the type of person, she says, hey, hold on a second, is everything normal here or not? And then she continues. And that is the attitude that you need to have. Does that answer the question? Good.
Okay, another question over here.
Well, since you have been an astronaut, can you tell us what do you need to become an astronaut? And since you are the one person here in the room which has been in space, what did you change after you came back to regarding to our Earth?
What did I change?
Yeah, in your life to save our planet, or?
Well, first of all, what do you need to become an astronaut? Things are changing. When I was elected, it was there were only two paths, which is either you were a pilot, a test pilot, or you were a scientist, physicist, chemist, biologist, engineer. But we will see in the future completely different professions as well. So I am quite confident that space will open to many more people, even without this background. If you want to become an astronaut with NASA or ESA, this might be for the next 10 years or so still be the only venue. With respect to the qualities that you have to bring with you, first of all, your brain needs to be hardwired in a certain way, which means you need to be able to absorb a lot of information in a short time, and out of conflicting information, detect the proper one. And these psychologists have devised tests where they figure these things out. But also there, I should say, I would never have become an astronaut in the 60s of the last century. So we have learned a lot because the requirements changed and allowed me to become an astronaut, and the requirements will further change and more people will become astronauts. So it will not, it's just the same thing like pilots. In the very beginning, these were very special people, and today you have to have certain qualities. I mean, if you can't add 2 and 3 together, it's probably not a good plan to become a pilot, but with a good background, why not become a pilot, for instance? Things are changing. What have I done differently? I don't know. I am not aware that I specifically have anything in particularly done differently. I rephrase the question, did it change you? And the answer is probably not. Why? That is difficult to tell, but the person that you see now in front of you at 60 plus is not the same as I was when I was 40, and the 40-year-old was not the same as the 20-year-old. And the development that you take over these times, you take in small little steps. And which step is responsible for what development is very difficult to tell, even when you are looking back. And I can only tell there were more prominent things in my life that affected it more than the space flight. That is the best answer that I can give you. And if I ever had tried to get airy or so, there were at least 4, if not 5 people pulling me back down and down to earth again. It's the best answer I can give you.
Any other questions? Yes, over there.
Hello. Your lecture was really entertaining. Thank you for that. I have a question about the light, the blue light you show us that was caused because of the oxygen molecules. And my question is that, did you see it for the entire day or just a fixed amount of time in a certain day? Did was there any schedule of it?
The green, the air glow?
Yeah.
No, we saw it. I am not sure. I can't say you now that we saw it from sunset to sunrise, but we saw it every night.
The light, the blue light you showed us because of the oxygen molecules or something like that.
No, the oxygen molecules were the green light.
But there was a green light you showed us. Just, I don't know, in some slides back.
Maybe you can tell us which picture it was.
Yeah, this one.
This one?
Yeah.
Yeah, this is green light.
Yeah. I just want to know that how frequently you see it.
Pardon?
When did you see it? It was for the entire day or just a glimpse?
Not during night.
During the night?
You see it only during night. During the daytime, the oxygen absorbs energy by the sun. And then during nighttime, when there is no sun shining on the oxygen atom, it falls down from the higher energy level to the lower one and emits green light. Yeah. But I can't tell you now that the moment the sun was setting that we saw it. I was not staring outside the window all the time either, but I do not remember that I haven't seen it when I looked out. Let's put it this way. Yeah. Here was a question. First lady, thank you.
Thank you. Your lecture was really enlightening. Thank you for that. And I actually have 2 questions. The first one is, not about the picture, sorry. How did you train to not survive, but to handle zero gravity? Like, how did you and your partners train at NASA? And the second one is, I missed the first few minutes, so I was wondering about the selection process of NASA. Are they like, we want you, so they are selecting you, or were you applying like you wanted it and just hope for the best that you were chosen by them?
I start with the second one. No, I wanted it, and so then you apply, and I was at the right spot at the right time. Yeah? So that's it. I mean, I was lucky, to be honest, because in the selection process where I was selected, there were in the end 13 candidates. And they could have, if you ask me, they could have just put the 13 names on the dartboard and throw the arrows, and there where the arrow hits, you are an astronaut. And they would have been just fine. Now they selected 5 out of the 13, and I was one of them simply because I don't know what. Maybe someone liked my nose better, or I was given the right question and someone else was given the wrong question. You never know how these things go. I am not saying that well, I was responsible for the last ESA astronaut selection, so I was the program manager, and I asked the team, how do we find the best astronaut in Europe? So they were thinking, and after, I forgot, 5 minutes or so, I said, what is your answer? And they gave me answers, and I said, I have another one. My answer is, there is no best astronaut. Doesn't exist. So let's not look for something that doesn't exist. Let's look for a good person who can do what we are asking. It is not important that we find the best one, because the best one does not exist. We have no clue what kind of situation someone will face, and we may be lucky that we have selected those people who can master them, but there might be a situation that no one can really master, and then did we do a bad job? Not necessarily. So in my humble opinion, we had in the end 22 who were simply excellent, and out of those 6 were chosen. So that is the way to look at it. And how do you train for zero gravity? You cannot. You actually cannot. There are certain things like parabola flights, and I talked to a young lady about those. I did 1,200 of those. So I had more than John Glenn zero-G time in his first 3 revolutions around the Earth for 4.5 hours. 1,200 is much more than that. But it's different. And essentially, your body takes some 3 days, I say. The adjustment is not something that happens like a switch. Oops, now I am adjusted, just like the light is now on. It is a process. And you have a steep learning curve in the very beginning, but after 3 days, I think you're doing already very well. And after 5 days, you feel at home. And that was for me the biggest surprise, because I was 46 when I flew into space, which means my body was only used to gravity for 46 years. Now I am 5 days up there, and I have forgotten what gravity is. Intellectually, I remembered it, that there exists something like that, and that when I change, for instance, the lens of a camera, I just not dismount it and let it here and take the other one, and then not a good idea to do down here. But this is how we worked in space, constantly. And as I said before, you lost something, you look for it, you just turn around, and you find it, here it is. So it is really amazing how that happens. Now, Thomas Reiter, who has been in space twice for 6 months, I asked him, when does that continue? And he said, to some extent it is okay that after 5 days you are pretty much okay. But if you go to the International Space Station, which is now big, really big, with a lot of equipment, he said after 6 weeks you know where everything is. The shuttle is small, you know. You better know when you are up there where everything is, because you need everything and you may need it now. but on the station there's no way that it's as big as a soccer field. So it is impossible that you know where all the tools are and every little detail. You have to learn this process. And he mentioned to me, after 6 weeks, you know where everything is. So this feeling, not only my body is there, but I know where, if I have to do something, I just go there without looking into the procedure. What do I need to do? That happens after 6 weeks, apparently. But body-wise, 5 days, I think, is a good number.
Okay. Thank you very much.
Okay, I think we have a question on the left side here.
Thank you so much for such a wonderful presentation. I am Mohammed Irfan from Pakistan. I am a student here. My question is, what was the biggest change in your perception after coming back from space?
I don't think there were so many perception changes. It is often said that going into space is such a unique thing that necessarily your perception must change. I'm a little bit reluctant to admit that. What I believe is, and sometimes you see it indeed, is the things change because when you come back from a space flight, everyone holds a microphone under your nose and they ask you about all kinds of things. And initially they ask you, how is it going into space and coming back and so on. But all of a sudden you get questions, which political party in Germany is the better one? And then if you think that because you have been in space, you have a better answer than someone else who has not been in space to such a question, and you give it, then you are simply stupid. Yeah? That is, but of course, it is nice, you know, I admit it, if people are interested in what I am doing and invite me to come here to Ilmenau, I say yes, I am happy to share my experiences with you. That is, it would be worse if no one would be interested in what I have done. So that is something that I enjoy, and I admit it, and I hopefully you notice it, that I enjoy it, talking about it, for your benefit as much as for mine. But it is, in my personal opinion, it is not a life-changing event. That is what I said before. It's not a life-changing event.
Thank you so much.
Since we heard now how it is to get rid of gravity, I wanted to hear how long does it take to actually remember not to drop the lens, and maybe also some insights from how your colleagues from the ISS are experiencing that. How long are they dropping the lens? How long do they need to readjust to gravity?
Yeah, the adaptation process when you come home is of course an interesting one. The shortest answer I can give you is the number of days you spend up there is probably the number of days you need down here to recover. Now that is a very cross rule of thumb thing. It is not entirely true, but the first thing that you notice, of course, if you have been only 11 days, in my case, absolute weightlessness. I mean, it is unbelievable. You feel absolutely nothing. Now you all feel pressure at your bottom or at your back. When you lie in your bed, you always have pressure points. In space, you have nothing. Absolutely nothing. I once made a small experiment. We had sleeping bunks with our sleeping bags, so normally we go inside the sleeping bunk and close the door so that it is quiet. But I said, well, I go to sleep by just staying there in the middle, in the mid-deck. The three, Dom, JV, and Mamoru were working on the flight deck, and I just tried to sleep in the middeck without, and I was very gently floating around. And the only thing that you feel is that you are breathing. You just feel the air going in and out again. Otherwise, and on the dark side, you don't even see anything. That is really interesting. Yeah? And I fell asleep, and then I almost said I crashed with my head somewhere, which is not true. I very gently got stuck somewhere, and I figured out, and then I floated into my sleeping bunk and continued to sleep there. Being up there is one thing. Coming back, gravity all of a sudden has something to do with gravity. I mean, it really pulls you down, but not. I mean, more than you would hope initially. We have a G meter that tells us what is the gravity right now as it increases, and when it was at 0.2, 0.3, so 20–30% of the normal one, I said, this is just right. But it continued to grow until 2 before it went back to 1. So we had to suffer a little bit coming down, and the nice thing was we landed, and I was not on the flight deck, but with JV, I was on the mid deck for the landing. And we were the first ones to get out and do already some stuff in the mid deck, while the crew on the flight deck was still busy with shutting down the shuttle and everything. So JV sits here, I sit there, and we get the go to stand up, and JV stands up and stands in front of me, and I try to get up, and oh my goodness, what is this? Unbelievable. And here she stands and smiles at me, and then she said, Gerhard, it's a little bit easier if you unbuckle first. Happens. Now I silenced everyone.
Okay, I think we have time for one more question up here on the left. Did you have a question? Quick question.
Thank you very much. I have a question that we have grew up with the fact that United States or the Americans were the first to step on the moon. And years after, they were saying no, it was just a fake things happened, and it was something turned in United Kingdom, and even the director of that scene dead or killed. So just I want to know what's your point of view about that. Is that real that Neil Armstrong was the first human who stepped on the moon or not? Thank you.
Well, I have my own Gerhard answer. Of course, I believe that they were on the moon, but the real reason, if I would have ever doubted it, I never doubted it, but if I would have doubted it, I had the chance to talk to almost everyone who walked on the moon, who was still alive at that time. I missed Gene Cernan. He's the only one, and now he has passed away, so I will not have a chance to talk to him, but I talked to everyone else. And to listen to them and see the sparkle in their eyes when they talk about the moon, you cannot have that sparkle if you have done that in a studio. That is the best answer that I can give you.
Okay, I think that wraps things up. Thank you once again to astronaut Gerhard Thiele. Big round of applause. And of course, we have a little something for you here to take home and enjoy.
Ja, sehr gerne, danke. Schokolade, wunderbar.